seminar. I'm glad to start out today's seminar. Our speaker is Vladimir Protasov from the Moscow State University, and he will tell us about the Newton aerodynamic problem after 300 years all over again.
Okay, thank you.
Let's welcome.
So do you see my screen?
Yes, we do.
Okay, and please also, what about this?
Okay,
so this is the first slide. Okay.
Yeah, okay.
So thanks very much for inviting me for this seminar. Today we take a look at one of the very intriguing problem of the optimal control of optimization and differential geometry of the end of 20th century, and it's still developing now. This is the Newton aerodynamic problem. The argumentation will be completely elementary, and so please don't be afraid if you forget something from differential geometry or from optimization, because no special knowledge is required. So everybody who went through the standard program of the first 2 years of education in Moscow in mathematical department will understand it. Well, in 1686, Isaac Newton published his Principia in Philosophia Naturale. In that book, he formulated, this is a 3 volumes book, and he formulated the main principles of mechanics, 3 main principles of mechanics, and plus the gravitational law. The first principle was given earlier by Galileo Galilei. The second 2 principles, which we call now the second and the third principle of Newton, were first formulated there in that book. And it's interesting that we have to be thankful for publishing that book, not only to his author, but also and mainly to another person, Edmond Galley, who is a comet of Galley, who just put some pressure on Newton to write a book, to publish his results. I believe that most of us do not like to write texts, especially long texts, especially survey papers or books, because we all want more to solve problems. At least, well, when we are young and we are full of forces. So all of us postpone writing books till the pension time, till the time of retiring. And more or less the same, probably Newton desired to do more or less the same. So he was not yet 40 when he started writing his Principia, and he wouldn't do that. If Edmond Galley will not just press him, saying that, well, you have to do that. So you have to write all your results before you forget, because Newton wanted more to solve problems and to do further research. So also Edmond Galley, he has some administrative tools. He worked in the Presidium of Academy of Science of Queen's Academy of Science and so on. So at any rate, it took Newton several years to write these fundamental volumes. And in the end of the volume 2, he put several examples of application of his laws of classical mechanics. He formulated several very almost applied problems and showed how they can be solved by newly opened, newly discovered laws of mechanics. One of those examples was the aerodynamical problem. So in the second volume of Principia, Newton formulated this problem and solved it and got a complete solution. And now the solution of Newton have entered more or less most of textbooks in optimal control and calculus of variations. And strangely enough, after 3 centuries, it became clear that the solution of Newton is not completely correct. So actually, almost exactly 300 years after Newton, in 1989, one example appeared, a counterexample appeared to Newton's main theorem. And so after 3 centuries, the problem is still open and has to be solved all over again. How could it happen? And in general, it's a philosophical issue. Do genius make mistakes? We will see and discuss it. The aerodynamical problem is formulated in the following way. So we assume that some convex surface moves in a uniform, inviscid, incompressible media of 0 temperature. So first, this media consists of particles which are unmoved. So stable unmoved particles, all particles assumed to be of the shape of spheres. And there are no some other forces except for the force of heating of the surface by those particles. The media is supposed to be quite sparse, and it's assumed that the particles do not hit each other, but hit only the surface. And the moving is with a constant velocity and the constant direction. So we assume that this particle goes with the constant speed, and in this uniform media of ideal media and the 0 temperature. The problem is to find the smallest possible resistance. What is given? So first of all, it's quite natural to give the form, the shape, and the sizes of the base of the surface. Of course, the bigger the base, the bigger the resistance, and that's why we fix the form and the sizes of the base. And Newton considered the simplest case when this base is just a disk of a given radius r. Then it turns out that the height must also be fixed. This is not that obvious, but as we will see later, if height increases, then the minimal resistance decreases, and if the height goes to infinity, then the minimal resistance goes to zero.
Excuse me, do you have any concrete formulas for resistance or for people who are not physically oriented?
Yeah, the formulas will follow, of course. So the resistance is just a force. There's just a force of resistance. Yes. So we can imagine that our surface moves in the media like in a gas, very sparse gas, and there will be some force of resistance, and we have to compute the minimal force of resistance depending on the surface. So we want to find the, let's say, the surface of the optimal shape for a rocket, for a car, for a ship, for example, if we sail on the sea. in order to have the smallest possible resistance. We will first we will start with deriving that formula, of course. Well, so we need to fix the base, and we need to fix the altitude. Under these two assumptions, we can already formulate the problem. Among all the surfaces with a given base in the shape of a disk of a given radius, and with the altitude, with a given altitude, we need to find the surface with the smallest possible frontal resistance, moving in a sparse media. Newton made a very natural assumption that this resistance should be some surface of revolution, and this will be a revolution of a graph of a function. This function will be denoted by f of x, and what can we say about it? First of all, it's convex, and second, it's increasing. Well, and so the problem becomes one-dimensional. So this problem becomes univariate. We need to find the optimal function, optimal univariate function f of x, in order the corresponding surface of revolution have the minimal frontal resistance. And our condition now read that the projection of this surface onto the OX axis is given to R, and the projection to the OY axis is given to H. Well, we see that among all functions, all convex increasing functions, we need to find an optimal one. Let me immediately emphasize that the answer will be non-trivial. So this is neither a linear function, no parabola, no. This is a function which appears, I believe it appears first in the answer for the Newton problem. First of all, let us derive the formula for the resistance. Of course, we split this graph of this function into many segments, into many straight pieces, and we need to compute the resistance of each part of each piece. Well, assume what we are going to do is something like the way of deriving the main formula for the main law of thermodynamics, which was in high school. Yes. So, well, in the standard textbook of physics in the high school, there was a proof of the main law of the thermodynamics. And we will do more or less the same technique, and I believe this technique will be familiar to you. Well, first of all, what kind of force causes the resistance? Of course, this is the force made by heat of one particle. It heats the surface. Why does this particle act on the surface? Because the impulse of the particle changes. And the change of impulse, as we know, is equal to the force divided by the force multiplied by the period of time. So we fix the period of time t, and we compute the total force during that time. So we see that the force of one particle is equal to the variation of its impulse within the time t over t. Okay. So to compute the variation of impulse, well, this is simple because this is the change of velocity times the mass. Let us emphasize that the change of velocity, first of all, it is meant in the vector form. So this is the difference of two vectors, because the absolute values, of course, of two forces before hitting the surface and after hitting the surface, the velocity stays the same because of our assumption. So this is the heating of a surface without And another thing is that we use the symmetry. Our surface is symmetric. So on the right, we will have the same function, where we can take the same particle. Therefore, using this symmetry, we understand that the horizontal projection of the change of the impulse disappears, because these are two vectors looking in opposite directions. And therefore, we need to compute only the change of projection of the impulse to the vertical axis. Well, this is a simple geometry. The initial impulse is equal to the mass times velocity v. As for the final impulse, the projection of the final impulse is equal to the same velocity times cosine of the angle. Well, we denote by alpha the angle which makes the chord AB with the OX axis, with the horizontal axis. In this case, the angle between the final velocity and the horizontal direction is equal to pi, minus 2 alpha. And eventually we get that this projection is equal to minus v times cosine of 2 alpha, where alpha, let me repeat this. And now, using the formulas of trigonometry, we see that this change of the impulse is equal to the following value. This is cosine square of alpha. So mv times cosine square of alpha times 2. This is, and we divide it by t, and we get the force caused by one particle. Now we need to multiply it by the total number of particles. This is also simple, because all particles which can hit the surface within the time t form the following parallelogram, with the heights equal to Vt. Here, let me stress this very important moment. Here we assume, we use the assumption that the particles are unmoved and the surface moves with the constant direction. We can we can relate the coordinate system not with the particles, but with the surface. And in this case, we can imagine that all particles move up on the same direction with the velocity v. So in this case, all particles inside this parallelogram will hit the surface. Once, exactly one time, in the period of time t. Now we have used the assumption that of zero temperature. Particles are unmoved, so there are no other velocities of this particle except for the constant velocity v directed vertically. Therefore, the total number of particles is equal to the density. By the density, we now mean the number of particles in the unit of the volume. So the density times the volume. The volume of what? Not of parallelogram, because this must be the three-dimensional picture. But we need to compute the volume of the following figure. The figure formed by the rotation of this parallelogram about the y-axis. We consider the rotation of this parallelogram, this strange figure, so like something like cylinder, but not quite the cylinder. How to compute its volume? Well, approximately this volume is equal to the product of the area of the parallelogram times the length of the surface. The length of the surface, the length of the circle. On the circle of the trajectory of this point, of the point of midpoint of the segment. Of course, this is not exactly, but approximately if the segment is small enough, so approximately the volume is equal to the area of the parallelogram multiplied by the length of the circle. And the length of the circle is 2 pi times this distance, and this distance is x. So we need to multiply our function, our force of one particle, by the total number of particles. And we multiplied by the length of the segment, which is, so the area of the parallelogram is Vt times dx. Dx, this is a small, this is the small step size. This is the small width of our parallelogram. And we get the following formula for the total number of particles. And finally, we see that the total force is proportional to the following value. The loss of impulses of all the particles is proportional to mass times v squared times t cosine square of alpha. And then we need to divide it by t. So this is the formula for the total resistance. Of course, I divided it by 2 pi. Well, we can already make some observation. For example, the force is proportional to the square of the velocity. We just proved it. Of course, this was known long before the work of Newton. Just all specialists in ballistics knew that for centuries. And it's also proportional to the cosine square of alpha. And we see that this is the resistance made by a small segment on the graph, the revolution of this segment about the vertical axis. So this is the total resistance made by this ring, this like this strip, this, and now we have to add, we have to compute the summation over all those strips, and we get the following formula for the total resistance. C is some constant. C doesn't depend on the surface. It doesn't depend on the graph of the function. This is m times v square. And actually the main part, the main hero of our investigation is the integral of the cosine square of alpha of x. Where let me recall, alpha is the angle made by the tangent line at our point x. So this is x, f of x. We draw a tangent line through the point x, and this is our angle alpha. Of course, alpha depends on x. We draw the tangent through every point of a graph of the function. We have the angle alpha of x, and we integrate this value. This is the formula for the total resistance, and we want to minimize it. Well, so the aerodynamic problem is formulated in the following way. This is the traditional way to, this is traditional form of calculus of variations problem. What is the difference of calculus of variations from usual problem of finding maximum and minimum? If you want, for example, like in the first year of mathematical analysis, if you want to find the minimum of some function, we compute the derivative and put the derivative equal to 0 and so on. This is a univariate problem. If the problem is multivariate, so we put all partial derivatives equal to 0, or in other words, the gradient equal to 0, and we solve the corresponding system of equations and find the point of minimum. In the calculus operations, we need to solve the problem not over finite dimensional set, but over the infinite dimensional of the set of all functions. So among all functions f of x, which are increasing, non-decreasing functions with the given boundary conditions, so among all functions connecting 2 points, we need to find one which minimizes this integral. This is the classical problem of calculus operations, and there are classical methods to solve it. Unfortunately, here we have some condition which is not quite admissible for calculus operations problem. This is the condition given at every point. We need to solve our problem not among all functions, but among all non-decreasing functions. This means that the derivative is bigger than or equal to 0 at every point. That's why we have to use not the technique of Euler-Lagrange, elaborated in the 18th century, but more, let's say, modern results of the methodology of 20th century. And this is the so-called Pontryagin maximum principle. We are not going to penetrate all the details, but we just see how such problems can be solved. First of all, what is cosine square of alpha? Well, cosine square of alpha, of course, can be expressed by the tangent of alpha, and the tangent is equal to the derivative. So that's why we make the following change of variables. We denote by u the new variable, which is a derivative of a given point. And that's why cosine square of alpha will be equal to 1 plus over 1 plus tangent square of alpha. And the tangent is equal to u, so this is a derivative. And in terms of u, we obtain the following expression for our objective function. So the total resistance can now be written in this compact form. And the non-decreasing condition means that u takes arbitrary values from 0 to plus infinity. We have rewritten our problem. We only mentioned that we are going to use this Pontryagin maximum principle, the simplest version of it, which is really simple, to use this change of variable is quite standard, and u usually called is control. This is the control function. Why is it called control? This is because of the sense of problems of optimal control. We are not going to discuss it now. This is this variable is called the optimal control. You may wonder why the control variable is called u, not c, after the control. Well, because Pontryagin with his colleagues, young in that time colleagues, Boltyansky, Mishchenko, Domkrelidze, they call it U after the Russian equivalent of the word control, управление. Well, how many mathematical terms do we know which are originated from Russian language? Not so many. I know only the Russian letter P for the angle of the parallel line, the minimal angle of the parallel line in Lobachevsky geometry.
Well,
now we see that
maybe perestroika in singularity theory.
Probably, yes. And this is U, and this is a control, управление, was named by the authors of Pantragen's maximum principle. Here in this problem, the principle is formulated very simply. We have the objective function, and we have the condition. Now let us remember the Lagrange multiplier rule. If you want to minimize some value under the constraint, for example, the sum of values is equal to a constant, or product of some values is equal to another constant, and so on. We do the following. We consider the sum of the objective function, it's here, plus the constraint. The constraint is U, so U must be non-negative. And that's why we have to multiply this constraint by a number. We call this number P. Usually this is called after Pantragen, P. Well, so this is the objective function plus the constraint function. The constraint is U because we made the only constraint that U is non-negative, times P times the constant. And the Pantragen maximum principle says that if the function x if the function f of x provides minimum for our problem, then at every point x, this value must be minimal for any choice of u. Once again, so assume the function f of x is optimal. So assume the function f of x gives the solution of our problem. So for this function, this integral takes the minimal value, where u is just the derivative of our function f prime of x. Then, at every point x, the number u is a point of minimum of this function. Let's call this function L of u. The number u of x is the point of minimum. So u of x, which is f prime of x, is the point of minimum, argmin, of the function L of u among all non-negative u. For every concrete point x of the segment from 0 to r, the function L of u must be minimized. So for every point, we choose u in this optimal way. In this function L of u, x is given. P is a constant, so P doesn't change at all. So only u is a variable, and we need to find the minimum of this variable. P is a constant, and this is a parameter, which is unknown, but this is the same for all x. X changes. So x is an arbitrary number from 0 to r. Which is not a surprise, because for every x, we have its own problem. We have its own problem of minimizing one function, and therefore, of course, u of x depends on x, which is very natural. Now we need to solve this minimization problem. It would be now more convenient if I write something on this whiteboard. So L of u is equal to, excuse me, L of u is equal to x over 1 plus u squared plus pu. P is non-negative, this is what we know. X is from 0 to r. For every x, the graph of this function looks as follows. If at the point u is equal to 0, the first term is equal to x, the second is 0, so we have here x. Then it's seen easily that in the small neighborhood of x, the function will increase, that it will be decreasing up to some moment. And then asymptotically, it turns to p times u, because asymptotically where u grows, this tends to 0. That's why it has an asymptote, the line p times u. It's easy to show that there are only 2 points of 2 stationary points when the derivative is equal to 0. And of course, the first point provides local maximum. We need the point of local minimum. This is u min. We see that actually the point of minimum, u of x, can be either 0, it can be either in this point, or in this point. So this is either 0 or u min. The point u min is a solution of the following equation. L prime of u is equal to 0. So there are only 2 opportunities for every x. For some x, this point is the value of this point is bigger, and the answer is given by the point u min. For some x's, we have an opposite situation. So for every x, we have one of these 2 answers. It's easy. It is a simple exercise to write the derivative. This is minus 2xu over 1 plus u square and square again plus p is equal to 0. So from this we find u min. Well, now unfortunately we see some trouble, because for every x, we need to solve this equation. We need to find u. But this is an equation of 4th power. And because u square and u square here. And the equation is quite non-trivial, because, for example, this is not b quadratic equation, because we have u, the first power of u. We should be careful here. We have part p times 1 plus u square minus 2xu is equal to 0. And we can understand now that we will never solve this equation. Of course, we could have used the formula for the for polynomials for the equations of degree 4, the Ferrari formula, but it's very technical, as we know. And that's why we take another way. We instead of expressing u, we express x. X is equal to p times 1 plus u square over 2u. And now it is equal to, we just open the brackets, p over 2, 1 over u, plus 2u, plus u cube. So we did something opposite. We use u as a parameter, the main parameter, and we express x. If we can express not only x, but also L of u, but also the function f, then we are done, because in this case, our graph of our function will be given as a parametric curve with a parameter u. Well, how to express f of x? It's simple, because we can express instead the derivative of f with respect to u. By the chain rule, this is the derivative of f with respect to x times the derivative of x. But the derivative of x is nothing but u. So we have u times the derivative of x, f with respect to x. And this is no, f of x is u, of course. F of x is u by definition. And x prime, the derivative of x with respect to u, is readily available. Because this derivative, because we have an explicit expression of x, we can differentiate it. So we see that this is x, this is u, times the derivative p over 2, and now we have to differentiate. 1 over u gives minus 1 of u squared, plus 2, and now we have to differentiate u cubed. This is 3u squared. Well, and everything which should be done now, which remains to do, is to compute the integral of this expression. So we express x and we express f. Which means that in our curve, in the graph of our function, for every u, we have x of u, y of u. So this means that we have found this curve parametrically. After that, it will remain to revolve it with respect to horizontal axis and get our desirable surface of the best approximation. Unfortunately, already in this stage, we have some unexpected trouble. Well, first of all, how to understand this 1 over u, because if u is 0, for example, so we have something like division by 0. Yes, so we have, well, this means that u cannot be equal to 0. But on the other hand, at some point, u is equal to 0. This implies that actually the answer to our problem will be given by two different situations. First, when u is equal to 0, and then when u is given by this form. This is the answer. So this answer is actually
excuse me.
Yes.
Oh, I think your demonstration is disconnected. Oh, sorry. Yeah.
Yeah. So let me again. So I share the screen. We have our curve, our optimal curve. So do you see the screen? Do you see the slide?
Yes.
Okay. So our optimal curve is given by a parametric curve x of u, y of u, but only when u is not equal to 0, because as we already noticed, u can be equal to 0, and actually u is identical 0 in the very beginning, from 0 to the point 2 pi, to p, after which it goes up, strictly increasing, along the curve we just found. This is x of u, y of u, where x and y are given above. This is what we have proved. This is so-called switching point from 0 to another curve. And this point is characterized by the property that the angle between the tangent line at this point and the horizontal axis is equal to 45 degrees. So this is the answer. And then we consider the revolution, the surface obtained by the revolution of this graph by the vertical axis. Well, of course, everything depends on the parameter p. For example, for small p, the surface looks like this. This straight segment in the very beginning, after the revolution, becomes the flat part of the surface. And this flat part, if p is small, then the flat part is small. If p is large, then our surface becomes very wide. It looks like frying pan. The answer is a bit counterintuitive. We've never seen any rocket with the obtuse end. So it looks a bit strange. So the end of the surface of the smallest resistance must be sharp. This is our intuition. But actually, this is not true. And the surface of the smallest possible revolution has this obtuse end. Well, and especially this looks very controversial. So how is possible then this surface will have the smallest possible resistance? Well, but this is true, at least by the solution of Newton. So this solution is correct. And of course, it entered all the textbooks in optimization and extremal theory and so on. These are several examples of our surface. Here p is equal to 2. Here p is equal to 1. And here p is equal to 1/2. For every p, we have a different form of surface, but all those forms are obtained by the same solution, by the same form of the solution. And the minimum is unique. Moreover, it's not difficult to show that this is indeed an optimal form. So actually, the Pendragon maximum principle gives only necessary condition for minimality. The situation is very similar to what we have in finite dimensional problems, extremal problems. For example, the derivative is equal to 0. This is only necessary condition for minimum, not sufficient. In the classical, trivial example of x is equal to x cubed. For x is equal to 0, the derivative vanishes, but this is not even a local minimum. For the Pendragon maximum principle, we have the same situation, but in this case, it's possible even to, by some simple trick, even to show that this solution is optimal. And this is a really sufficient condition. The problem is solved. 300 years have passed. And now what could happen? G.Butazzo and D.Kawohl. Butazzo is from Pisa, Scuola Normale di Pisa, and D.Kawohl from Köln. In 1993, they constructed the surface of the whose resistance is smaller, strictly smaller than what the surface constructed by Newton. This is an interesting story because actually the construction belonged to another person, G.Butazzo. He was a student, diploma student of G.Butazzo. But as far as I know, he didn't want to stay in academia. He didn't want to stay in mathematics, and that's why he constructed the example. Of course, G.Butazzo already had some ideas in his mind and so on. So G.Butazzo actually was the first to construct it. He was just a student. But then he refused publishing it. And his solution, the solution of G.Butazzo, with the reference of G.Butazzo, of course, it appeared first in the paper of Butazzo and Kawohl. Of course, this paper made a great sensation. My question is, how do you think how is it possible? This is the solution of Newton.
Maybe something at zero happens.
Well, how do you think what could happen at zero?
Well, you told that there should be a minimum either at zero or at x min.
Sure, yes. For small p, the minimum is zero. Then we have one switching point. And after that, we have the surface of this form. And after that, we have the surface of this form. Moreover, it's possible even to prove that actually this function gives the surface of revolution of the smallest possible resistance. But in reality, there are surfaces with a smaller resistance. In which place did Newton make a mistake? There was no mistake in the solution, but the mistake was principle. This is the matter of physics, of course. We could say that, well, the assumptions of Newton were too strong. This is like a classical anecdote about the white spherical horse going in a sparse media and so on. No, the reason here is purely mathematical. I will show you the example of P.Guasoni, and you will see the reason. It's here. We see that the surface of P.Guasoni doesn't follow the key assumption of Newton. This is not a surface of revolution. Very strange. We understand that if a surface has the circle in its base and the altitude equal to a given value h, then of course the smallest resistance must be achieved in the surface of revolution. This looks like an axiom. This is absolutely undiscussable. But in reality, the smallest resistance is not achieved in the surface of revolution. And so the result of Newton should be formulated not that strong, so in a bit softer way. Among all surfaces of revolution, Newton's surface is the best one, that possesses the smallest resistance, which implies that actually the smallest resistance is never a surface of revolution. And the problem becomes unsolved. So after 300 years, when everybody was sure that the solution of Newton is correct. Well, of course, this is just an example. In reality, this is not the optimal shape either. What about the optimal shape? So the example of P.Guasoni, Butazzo, and Kawohl, it demonstrates only the non-optimality of Newton's surface. But what in this case, what is the optimal surface? Well, the general case is considered by solving more or less the same problem, with the only restriction that here we need to compute not the derivative of the function f, because there is no function f anymore. There is a surface. the surface is not obtained by revolution of a graph of the function. So there is no function f. And u is now the function of two variables. This is some surface with the base being a circle. This is some surface of some strange form. We do not know it, which one. And this is not a surface of revolution. And the minima, the optimization problem to be solved by Pontryagin's maximum principle now looks like here, like this. It seems that we are going to immediately solve it, and the lecture would end by this moment, but unfortunately not. The point is that two-dimensional problems are much harder. One-dimensional problems can easily be solved either explicitly or numerically, but as for two-dimensional problem, this is a separate branch of research. And even simply looking problem like this one sometimes assume very hard solutions. And this problem, this is still unsolved. What is known about this problem? The solution exists. So it follows from the convexity. The point is the set of convex surfaces equipped with the Hausdorff measure is compact. And by the compactness argument, we can easily derive the existence of the solution. Well, in general, there is no uniqueness. Why is the optimal surface not unique now? Well, because of the rotation. We can rotate the surface of Guasoni, and formally we get another answer, because the function of two variables, u of xy, will be different after the rotation. Of course, the shape of the form will be the same, but the function will be different. So there is no uniqueness. But it is proved that up to the rotations, the solution is unique. So the solution exists, unique. The next property is quite unexpected. At all points where our surface is 2 times differentiable, its Gauss curvature is equal to 0. What does this mean? This means that this means that our surface contains a segment centered at this point. At all points of differentiability, at all points of smoothness, where our surface is 2 times differentiable,
is there any chance to prove that the set of points when it's not differentiable is just a segment, nothing more?
No, this is not true. This is not true. And actually, this is a great problem. Now, let me also only recall that by theorem of Alexandrov, any convex surface is twice differentiable almost everywhere. So at almost all points in the Lebesgue measure, there are segments going through this surface. So in some sense, this surface consists of segments. This implies, by the way, that it is never surface of revolution. It is never surface of revolution. Let me give several examples. This is almost everything we know theoretically. How does it look, and what are the geometrical properties of this surface? There are lots of research now. Of course, the solution is obtained numerically by numerical computation. But this is an even numerically quite technical problem because the equation is unstable and so on. But the numerical computation shows the following, that if the height is quite big, if the surface is high enough, then it has more or less this form. This is not just a convex hull of a segment and a disk, like in the examples of Guasoni, but the kind of smoothified shape. But if we reduce h, then suddenly in some point, this segment becomes an equilateral triangle. This means that in the boundary value of h, between the segment and the equilateral triangle, there is no uniqueness, even in this, even with respect to the rotations. So if H is big, then these are numerical results. The surface looks more or less like this. This is a kind of screwdriver отвертка. When we now reduce H, it will look like that. So with the equilateral triangle on the top, then this triangle, if it's further reduced, H becomes the square and so on. And so we going down, we go through all regular polygons. And as a limit, we will have a circle, but only in the limit. This is what was proved by numerical computation. This is not proof theoretical. Well, this means that if we get rid of an assumption which seemed to be absolutely obvious, then we could invite new surfaces, we could invent new surfaces with a smaller resistance. For example, with this surface of revolution assumption, if we get out of this assumption, we get something which has a smaller resistance. Now let us try to do more, to make another step. And since now our lecture will be totally geometrical, there will be no formulas. All arguments will be geometrical and quite obvious. Let us now reject another property, another requirement, that the surface is convex. Can it be? Can it happen? Then the resistance of non-convex surface is smaller than the convex one. A simple argument shows that it can. Let me remember that the resistance of a flat piece of a surface is proportional to cosine square, cosine alpha square, well, alpha is the angle made by this plane, two-dimensional plane, with the horizontal plane. So this means that if we take the Newton surface, so that this is Newton's surface, and make a small rectangular not hole, but we remove some small cone from our surface. Of course, the surface will lose the convexity after that. The resistance will become smaller. Why? Because before the angle of our surface with the horizontal line was 0, and so the cosine was 1. Now, at every point, the cosine becomes smaller than 1. And so the cosine, let me put square here. So the resistance force is proportional to cosine square, and it used to be proportional to 1. Now it's proportional to something which is smaller than 1. So we see that making this change of our surface, we reduce its resistance. It's absolutely counterintuitive. We see that spoiling the surface, making it non-smooth, we manage to reduce the total resistance. And now my question to the auditorium. Let us make this hole very, very high. So let us make this angle alpha large. In this case, cosine square of alpha decreases and possibly decreases to 0. So does this mean that we can make the resistance of the surface arbitrarily large, just making this hole? Well, in this case, rather not, because once this cone becomes too high, and it will make hole on the surface here, which is prohibited by our assumption. By our assumption, our surface must have a base, circular base without holes. But in this case, we do another way. We, instead of making one triangle, with the angle alpha, we now make many triangles. And the angle at every point still equals to alpha. Now we can imagine what happens after we revolve our surface about the vertical axis. We will have something like that, something like a ribbed frying pan. If we look at the bottom of the frying pan, it looks like that. Yes, and here we need some triangle paths. And the resistance of the bottom of this frying pan is proportional to cosine square alpha. But now we can already make this alpha as big as we want. So our plan is the following: to choose some very small base of this triangle, epsilon, split the whole segment into segments of length epsilon, and for each epsilon to make this hole in the bottom. And after the rotation, we will have a surface of the total resistance close to zero. Am I correct? Is it really true that we can make resistance of every surface close to zero just by making such holes on the surface? It would be extremely nice, yes, if this was true. So in this case, we can take, for example, a car. I don't know, like Ferrari car, yes. Make all this terrible modification of its surface, making it extremely non-smooth, and the frontal resistance will be zero. Yeah. Is it a realizable plan? The main difficulty here is that after some moment, there will be no the main condition of the unique impact will be violated. We derive the formula of the total resistance, which is proportional to cosine square, under the unique impact assumption. Every particle makes a unique heat of the surface. Now it will be like two heats. And therefore, the proportionality of cosine square will not be true anymore. Well, of course, if alpha is not, so we are not able to make alpha is big enough. And actually, the sharp bound here is 30 degrees. So if the angle alpha is less than or equal to 30 degrees, then this is possible. In this case, the resistance, the force of the resistance is reduced by cosine square of 30 degrees, which is 3/4. 3/4 of the resistance force. Not bad, not bad. So we saved 25% of the fuel, for example, if we build a spacecraft or a plane, for instance, just making this ribbed surface. This is already true. Well, of course, nobody forced us to make these kind of triangles, and the problem became how to make these holes in an optimal way. They shouldn't be. Turns out that they shouldn't make. They shouldn't have shapes of segments. The shape must be the shapes must be of the form of parabola, and the main. The optimal coefficient of the reduction of the force is equal to this number, which is less than 0.75, like for the triangular case. But this is already optimal, and this is a maximum which could be achieved by this trick. Well, so we see that getting rid of the convexity assumption, we can already reduce the resistance, but not much. You see, less than twice, 0.64. To do the further reduction, we get rid of another assumption, connectedness. Let us make a surface which consists of two parts. And we will see that the total resistance can be already as small as we want. We use the following construction, which exploits the optical properties of parabola. As we know, if we take the focus of the parabola, then the reflected ray of light goes vertically for every ray starting in the focus. This is the optical property of the parabola used in parabolic antennas and so on. Pocket lights. Well, now we try to construct a parabolic surface as follows. We take a piece of parabola from the vertex of the parabola to the level of its focus. So this is the focus. Then we consider the homothety of this parabola with the negative coefficient. So this is the homothety plus rotation plus the symmetry about the focus. And we choose coefficient of the homothety very small, epsilon. So we have two similar to each other pieces of the parabola. Let's see the way of the rate of the way of one particle. The particle, for us now, it will be more convenient to assume that the particles go from below, not from above. So the particle goes down, makes an impact to the surface, and by the optical property of the parabola goes through the focus to the small piece of the parabola. And then, because this is a common focus of two parabolas, we apply the optical property to the small piece of the parabola. And conclude that the reflected ray goes down in the vertical direction. Well, so if we take an arbitrary particle, it either doesn't meet the surface, so in this case the impulse is not changed. If it hits the surface, then after two reflections, it does not change the direction of its velocity. So the velocity stays the same. It was v directed down, it becomes v directed down again. So you see that at any rate, the particle doesn't change its impulse. This means that there will be no resistance force at all, because all particles make the total impact zero. Of course, not all, because there is one exception. And this exception is particles hitting this small parabola. but we make the homotopy with the coefficient epsilon, so we can assume that the total resistance of this small part is less than epsilon, so the total area of this part. Of course, this is just a two-dimensional picture. To make it 3D, we need to consider the surface of revolution. So we revolve our figure, which consists now of two parts, with respect to the vertical axis. We obtain something like this. This surface consists of two parts. One part, the main part, is a parabola. It looks like a very sharp parabolic cone, the lower part, and the upper part is like a bell. Of course, belt. Of course, they should be connected somehow, so we can connect them by some very, very thin sticks, which make also zero direction. And this kind of surface will have the total resistance less than an arbitrary choose number, less than epsilon. So this construction, which belongs to Alexander Plachov, it was in the beginning of 2000, shows that it's possible to come up with the surfaces under the same conditions containing the disk of a given radius r on the base and the given height of the resistance smaller than any given number epsilon. Well, if we consider, of course, if we change the coordinates, making this picture a bit wider, of course, we can notice that this picture suspiciously reminds us something. It looks like, well, let's see. Can you see my screen now?
Yes.
Okay, because last time it was disconnected. Yeah, it looks like this. A form similar to one with the resistance with two parabolas, the flying saucer UFO. Well, who knows? Maybe this spacecraft of from other planets, maybe they have something of something similar, this construction. And in 2003, Alexander Plachov came up, he shocked the mathematical community, coming up with the surface of zero resistance. The construction is actually elementary, and it's even possible to show it in high school. We consider a triangle, isosceles triangle with angle 30 degrees, 30 degrees, and 120 degrees. Well, then we extend its lateral sides. We will obtain the same triangle, and then we make a symmetric picture in the right. Everything we need is to the first and the last triangle. So we have two triangles. If we now watch carefully the way of an arbitrary particle, we will see that for arbitrary particle, the velocity is not changed. The particle started with the vertical direction. It after two hits, after two impacts, it still goes in the vertical direction. So there is no loss of impulses. And this surface offers zero direction. Of course, after that, we have to revolve it, and we get this kind of surface. this surface, which already makes a hole. So topologically, this is not homeomorphic to a sphere, of course. But anyway, it has positive volume, and it has zero resistance. So this is possible to get surfaces of zero resistance, really zero resistance. And these surfaces have positive volumes because you see that this triangle, if you rotate it around the axis, so something can be put inside, and we can transport some non-zero mass, some goods we can transport in the spacecraft with zero resistance. Well, it's interesting that if we consider optical interpretation of this construction, taking a ray of light instead of the way of the trajectory of the particle, we have two reflections. So every impact becomes a reflection. And we consider two surfaces, not one. So one surface above and one surface below. And after two impacts, after two reflections, there are not two already, 1, 2, 3, 4 reflections. The ray of light doesn't change not only its direction, but also its position. The ray of light goes along this line, and it goes out of the segment along the same line. So this is the same line. This means that if we put something behind this surface, then here, if you put our eye here, we will see the surface completely, this object completely unchanged. So the surface is totally transparent, in spite of the fact that it's made of it's made of mirrors, parts of mirrors. So this is 100% transparent surface. An Invisible Man of Herbert Wells. Well, who read this beautiful novel remembers that the main hero made himself invisible by drinking some special potion. And this potion was prepared with some very special ingredients and organic, non-organic, and so with a special temperature. So he prepared some kind of drug, some kind of medicine, and used it, and became invisible. In reality, everything is much simpler. We should make a kind of, I don't know, kind of a coat, raincoat of this shape, and we will become invisible. We can, for example, we can hide in this triangle inside. So invisibility is possible. It's interesting that, well, these are positive results in a sense. There is one negative result in this direction. If we make this surface real, so if we pay money to some juveler who will make this kind of surface made of perfect mirrors and so on, to our surprise, to our disappointment, we will see that it's not transparent. That if we look by our eye from this direction, then we will see not exactly the picture. So the picture will be spoiled. It will be a bit modified. My second question, how do you think why? According to our result, so the picture should be totally the same because
I think because the angles of the triangle are not just perfect points. They have some, so they should have some size.
Yes, but this is unfortunately this is not the main reason. The main reason that we never look in the world by parallel pencil of rays. So our eye makes not parallel pencil, but pencil of rays going from one point. This surface is invisible by the parallel pencil of lines, see? But if you look through our own eyes, this pencil will go through one point. And unfortunately, this surface is really, it really possesses zero resistance, but unfortunately it's not totally transparent. Of course, the question arises, is it possible to come up with the surface which is transparent for pencil of rays of light going from one point? It's possible. I will just show you the corresponding example. It's here. Yes, it's constructed by an ellipse and by a hyperbola with the same foci. So this is possible. But now it also looks absolutely abstract, because this surface is invisible looking from this point, only from this point. From all other points it will be visible. But if you stay in this point, and if you close the second eye, so it's invisible from one point by one eye, not by two eyes. So it again looks, sounds like in that anecdote. But on the other hand, well, this is possible to do it with 2 directions, 3 directions, so on. And actually there are lots of problems arising in this way. For example, with non-zero temperature, with turbulence, with without zero impact assumptions, and so on. And we see that the aerodynamic problem, which seemed to be solved by the general belief, solved more than 300 years ago, after 3 centuries, it caused this blow of interest, and it's still under the tough investigation, and lots of papers published by the Newton aerodynamic problem. Still became it again became actual now. So I will finish on this moment.
Thank you very much for the great talk. I really enjoyed it. So there is one question on the chat, maybe not a question, but a comment. Newton's treatment on, do you see the comment?
The comment, let me see. Chat, let me see the comment. Newton treatment of this fluid problem seems essentially different from Euler-Lagrange's method, which assume the flow lines are all parallel on the surface, and then use Bernoulli formula. I think the Euler-Lagrange method is today's viewpoint. Well, not quite. This is one of this is one of the methods of analysis of this problem. Let me just stress that there are several statements of this problem. 7 statements came from physics, and each statement is of its own interest because it makes different assumptions and so on. But this, you are right in the sense that this such kind of formalization of our problem is also considered in the literature. Yes, this is true.
Okay, are there any questions or comments, remarks? Well, the topic is really very enjoyable. Maybe you have some formulations of problems which could be accessible, and maybe even for our mathematical circle, because we have lots of students who are interested in any source of mathematics, and maybe you have formulations of something. Well, in particular,
yes, of course. Yeah. Yes. Maybe I sent some papers to you as leader of the seminar. First of all, there is a very popular paper published in Quantum Journal. Unfortunately, it's only in Russian, by Plachov, Alexander Plachov, and myself. We published it 2 years ago. It's in 2 volumes of the journal. It's kind of survey, but very, very elementary for high school students. This is what can be seen as for beginners. Then there is a survey paper of Alexander Plachov, and also there are some open problems. Basically, in University of Aveiro in Portugal, sometimes new graduate school positions or postdoc positions open. Well, maybe even once a year, where there is a school of optimal control also interested in this problem. And if some of the participants have interest to that, they may maybe participate in the competition. So they always need interested students. But the problem itself, it seems to me very interesting and very promising. And you see that it has some direct applications and also very beautiful mathematics behind, beautiful differential geometry and so on. And some problems you see that they assume absolutely elementary solutions.
Okay. So, yes, excuse me.
Yes. Yeah,
no, please proceed if you have anything more to talk.
No, I finished, yeah.
Okay, any further questions or comments? Okay, thank you very much again. Hope to see you again.
Okay, so good luck.